Darcy's law is an important equation in the analysis of flow through porous media, and it's useful to understand where Darcy's law comes from when we go back to first principles. And so an approach is to take a look at the conservation of momentum and use that as a way of determining Darcy's law. So we'll start with a general conservation expression that says that in general, the source equals a divergence of flux plus a change in storage. So this is the source term here. This is flux, and C is the momentum per volume. So let's see. C is, well, let's write out momentum here is mass times a velocity. And C is going to be momentum per unit volume. And that's equal to density times the velocity, where this is rho is density, and that's mass per unit volume of the fluid. V is velocity of the fluid. So this is our general conservation expression here, and we want to determine these three terms: source, divergence of the flux, and storage change. So dc dt is storage change, the rate of storage change rate, and that's going to be equal to d rho v dt, just by substituting in our expression for C up here. The source of momentum, for our problem here, we will equate the source of momentum with the body force in the fluid, which is the density times G. I'm going to use this as the shorthand for the body force. The flux of momentum, there'll be, in general, we have two terms, an advective flux and a diffusive flux. And for momentum, the advective flux of momentum is going to be equal to C times V, which would be rho times V times V, the velocity. The diffusive flux, let's call this diffusive like. And to understand how this works, we can write the shear stress in the fluid. We could write it that way. That's going to be also equal to tau xy. You see shear stress written both ways. And in a fluid, that's going to be equal to the kinematic viscosity times the gradient in the momentum in the x direction. And the gradient is taken in the y direction. Okay, so this is looks like a diffusion expression in that we have a flux proportional to a gradient. Ordinarily, we would have a kind of our typical expression would be mass flux is minus d times the gradient in C, or in C, in concentration. We don't have the minus sign in this case, but we still have a gradient, and so the diffusive flux we'll say is equal to minus the stress in the fluid. This guy here is the kinematic viscosity. That has units of length squared per time. So it's working, this has the same units as diffusivity. So it's like a momentum diffusivity. And let's see, then we can have we put these together, equals the advective and the diffusive term, and that equals, so the divergence of the flux is just going to be the divergence of these two terms we just wrote. Okay, so we've got this general conservation expression here, and that's got a term here for the storage change. That's a term here for the source, and a term here for the divergence of the flux. Okay, so let's go ahead and substitute those terms in, and we'll go and just going to rewrite the expression that we started with, and then substitute in. Okay, so this is just in general for conservation of momentum. We can then use a kind of a simplified constitutive law for the stress in the fluid, and we can say that equals the pressure minus the pressure plus the shear stress in the fluid. And doing that and substituting it in gives us this. Okay, so this now is the Navier-Stokes equation, and it has these 5 terms. The body force, this is the divergence of the shear stress, which accounts for viscous dissipation from fluid friction in the flow. This is convective acceleration, pressure gradient, and this is unsteady acceleration. Okay, so this is a versatile equation and it'll handle a lot of different problems. For porous media, we're going to say that the velocity is slow, and that it changes, well, let's say the velocity is small and it changes slowly. So if it's small, then this term here, the convective acceleration, has velocity multiplied by velocity, so that's going to be really small, and we're just going to ignore it. And if it changes slowly, then this is the unsteady term, and it's a rate of change of the velocity, and so we're going to say that's just equal to 0 for this porous media problem. And then we'll also say that we're going to, right now anyway, neglect body forces. And if that's the case, then that can go, and we reduce it to this. Okay, so that's the Navier-Stokes equation with these simplifications. Now for porous media, we have to average this over the representative elementary volume. And so we write that like this, where these pointy brackets mean to take the average. Okay, well, the first thing we can do is say that this term here, the average of the pressure gradient, that just equals the pressure gradient. And we can see this if we take a small REV, or if the pressure gradient is changing slowly over the scale of the REV, then the average of the pressure gradient will just equal the pressure gradient. So that takes care of the term on the right side. Now, the term on the left side, we need to do some work with this. So here's what we'll say. The average of, this is the divergence of the shear stress, and that's averaged over the representative elementary volume. Now, the expression for the average is just the integral of the term we're interested in over the volume divided by the volume. So this is just the definition of a volume average. Okay, so we can make some progress here. If we go here to the next page, I'm going to rewrite this term. And that is, well, that's going to be equal to this. And from Gauss's theorem, in general, if we integrate the divergence of a flux over a volume, that equals the flux normal to the boundary over the area of the boundary. So here's the region. We've got some flux that's in here, and we take the divergence of that flux and integrate it over the volume, and that equals, this is usually it would be the normal outward, so this would be the flux dotted into the outward normal. Okay, so on this side, we've got the flux normal to the boundary, so that's the net flux into or out of the region, and this is the overall divergence of the flux. So that's what Gauss's theorem says, and using that, we can take our expression here, and we say then that this. Now, I'm going to introduce the porosity as the volume of the pores over volume total, and I'm going to have a simple conceptual model of a pore in a, so that's what I mean by volume total, and I've got the area of the pore. So there's area of the pore. This entire face here I would call area total, and we'll also have volume of the pore. And we're going to say, let's just say for purposes here that it's a circular pore, so the area of the pore is pi d squared over 4. The volume of the pore would be pi d squared L over 4. Well, I'm sorry. That's right for the volume. The area of the pore, the surface area of the pore, would be pi d, which would be the circumference of the circle times L. Okay, so if we go back up here to our integral, now, if we say that tau is uniform, then it comes out of the integral, and we just get this. And in that case, this term here just gives us the surface area of the pore. Okay, and that's going to be equal to the area of the pore, pi dl, and the volume of the pore, pi d squared L4. Pi's go, the L's go, d, and this is going to equal phi tau 4 over d. Okay, so that's the average of the divergence of the divergence of the shear stress, assuming that the shear stress is uniform over this circular pore. Now what we need to do is bring in a little bit more information. So the Hagen-Poiseuille law for flow through a pore or flow through a conduit says that the pressure gradient in the conduit, well, the length of the conduit, is something like this. Geometric constant, dimensionless. Mu, this is the dynamic viscosity. D is characteristic length. We could think of it as the diameter of the circular pore, and V average, it's the average velocity. Now, V average will be equal to Q divided by the area of the pore, where Q is the volumetric flow. So Hagen-Poiseuille will give us this. Okay, so that's one piece of information. We also put a break there. Now we want to go and look at the force balance. This is going to be some additional information. And we'll take a little bit of a slice, a narrow slice of the pore. So we've got a force going, F1 goes from left to right, F2 goes from right to left, and then we've got a shear stress on the wall of the pore, shown with the arrow down at the bottom. So from the force balance, F1 is equal to F2, and then that shear stress, that's a force per area. It's going from right to left, so we'd have tau times the surface area, which would be the circumference, which is pi d times delta x. So that's going to be delta x. Okay, so there's the force balance. For equilibrium, those have to all be equal. Now, the F1 is from the fluid pressure. So F1 is equal to P times the area of the pore. And that will equal F2. But, well, let's write it like this. There's F1. F2 would be equal to well, let's write it like this. F2 is equal to F1 plus df dx delta x. So the force balance is this. Okay, that's just this guy with these other relations substituted in. These cancel out on both sides. The delta x's cancel. Now, we've got these two approaches, the Hagen-Poiseuille and the force balance, both of which give us pressure gradients. So we equate them, and we get from Hagen-Poiseuille, we get this. And that equals the force balance, which would be minus tau for d. And this now gives us an expression for the shear stress. Okay? All right, so from the previous page, we have, okay, so we're going to take this expression and substitute in the expression that we just derived for the shear stress. All right, so we'll do that on the next page. Okay, so this is the substitution. That cancels. And I'm going to write this out again, where I'm going to write that. Looks like we got d squared. And I'm going to put in q AP. And let's go and take a look at that. So that's the porosity. And the porosity definition is the volume of the pores over the total volume. And what I'm going to assume is that this is equal to the area of the pores over the area total. Okay, so for that example that we just saw, where we have a cylindrical pore, it would work for that. And we're just going to assume that it works for the general shapes of pores. So if that's the case, then we can rewrite this like this. And up here, we had the porosity there, but I'm going to write the porosity out now as area pores over area total. So then these cancel, and this equals minus okay. So keep in mind the geometry here. We've got a block, then there's a pore in it, and we've got some volumetric flow going through that pore. This is the overall area. So by definition, the volumetric flow rate is Q over the area total. So this term here is volumetric flow. Okay, so we've got this. Okay, so that becomes this. All right, so we're getting there. Now, if we go back a couple of pages and look at what we got for the Navier-Stokes equation. When we were looking at Navier-Stokes, what we said was that that equals the pressure gradient. Well, now we have another expression for the divergence of the flux equals to this stuff. So we can write this. And we can solve for Q. This relates the flux to the pressure gradient. This is a form of Darcy's Law. We can rewrite it like this. So this term here is the pressure head. And we could write it, so K, where K is the hydraulic conductivity. So this gives us Darcy's Law as a pressure head gradient proportional to the flux that we get by starting with the conservation of momentum.